In this video, we're going to take this idea of comparing integrals in series one step further, so that not only are we going to check to see if an integral, or rather a series, converges, but rather we're going to be able to say when it converges, roughly what does it converge to. We're going to give a range of values where we can be 100% confident that the series must have an answer in between. All right, and so to motivate this, let's draw ourselves a picture. We're going to make this nice and big here. So let's suppose we have some function. We'll call that f of n, and we're interested in comparing the series whose terms are given by f of n to the area under the curve. So that's the comparison that we're going to use to come up with our estimates. And so let me actually put the curve in red. All right, so there's f of n. And it's very clear that the red area, the sum of n equals, well, 1 to infinity of an, has definitely got to be bigger than the red area, right? It's got to be bigger than the integral from 1 to infinity of f of n, just because the rectangles are bigger than the area under the curve. And so let me label these x values 1, 2, 3, 4, 5, 6, 7, and so on. Okay? And if we wanted to take this a step further, we could also come up with another estimate. We could shift all of those rectangles to the right 1 unit. And notice that what we're getting is all of the same rectangles except for the first one. And that's clearly got to be smaller than the area under the curve. And so if we start our sum with 2, we would be describing the blue region. And so more generally, we can say that the area under the curve from 1 to f of n is between the sum from 1 to infinity and the sum from 2 to infinity. All right, so this is similar to what we did before, but we're just doing it very generally. I haven't told you what f of n is. It's just some generic positive, decreasing, and continuous function. All right, so let's take this a little bit further here. Again, we're going to try to find adjust our statement to apply to the sum from n equals 1 to infinity of an, meaning we want to have some sort of upper bound that we can add to our equation here. And we can do that by modifying this inequality over here, because if we were to add a1 to both sides, notice that this quantity on the left-hand side is just the sum of all the terms from 1 to infinity. So that sum must be less than a1 plus the integral from 1 to infinity of f of n, or f of x rather, dx. And let's actually write that correctly. All right. And so now we know the following. We know that the integral of f of x dx is less than the sum. But we know that the sum is also less than what we'd get if we took that same integral and added the first term to it. And the only assumptions here are that f is positive, decreasing, and continuous on the interval that we're looking at. Okay? So we can say that not only that the sum must do the same thing as the integral, but we can say that it must lie between two values, and the width of that interval is just the size of the first term. Now, if that first term is large, this doesn't really allow us to narrow in very much, but we can easily modify this argument to apply to the sum starting at any value. So imagine that instead of drawing our picture starting with x equals 1, we started with x equals, say, 6. Well, we could still compare the black area, the red area, and the blue area. we could still do all of the manipulations that we applied before. The only difference is our integrals would now start with, well, 6, or in general, if we start at the kth term, we could say the integral from k to infinity of f of x dx is less than the sum from n equals k to infinity of an, which is less than ak plus the integral. All right, so we've derived a nice relationship that compares the sum to an integral, and we can now use this to come up with good estimates. So let's focus on a particular series. Let's look at the sum from 1 to infinity of 1 over n squared. This is a very famous series. It turns out that mathematicians actually struggled to figure out what this converged to for quite a while back in the 1700s. And finally, they solved this problem. It was actually Euler who solved it. And so we're going to try to not actually do what he did, which is get the exact answer, but we're going to try to get a ballpark estimate for this, since it is such a challenging problem. And I'll remind you what this sum looks like. It's 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25, and so on. All right, and let's suppose that we want to get an estimate. And we're comfortable adding up a few fractions, but we can't just go on forever. And so let's suppose that we use, we were interested in saying something about, we'll try to use S5 as our estimate. So we'll try to use the estimate 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25. All right, this is a partial sum with 5 terms. We might think maybe that's a good estimate for the total sum S, right? Maybe they're in the same ballpark. All right. So if that is our estimate, then we might want to know is how far off is it going to be? And the claim is that we can use this boxed result up above to help us. So let's look at the difference, S minus S5. That's telling us how far is our estimate from the true value. And if you think about the terms, S is all of the terms, and S5 is only the first 5 terms. And so if I subtract them, then what do I have? Well, I just have terms 6 through infinity. Agreed? So we can say something about exactly how large that is by applying this result that we just derived a moment ago. We can say that S minus S5, which is the sum from n equals 6 to infinity of an, and an here is 1 over n squared, has got to be greater than the integral from 6 to infinity of 1 over x squared dx. So that's this piece. And it's got to be less than a6 plus the integral from 6 to infinity of 1 over x squared dx. All right, let's evaluate that integral quickly. Integral from 6 to infinity, we can write that as integral from 6 to b, and take a limit as b goes to infinity. And antiderivative of 1 over x squared would be negative 1 over x from 6 to b, and we'll still take a limit. And plugging in, we'll have limit as b goes to infinity of negative 1 over b plus 1 over 6. And as b goes to infinity, you'll notice that term wants to go to 0, and we're left with 1/6. Okay? So that's our integral. And so 1/6 we know is less than S minus S5, which is in turn less than a6. The sixth term in our sequence would be 1 over 6 squared plus 1/6. And so what we know is that our error is between 1/6 and 1 over 6 squared plus 1/6. That's how far we are off. And in fact, if we wanted to get a better estimate, what we could do is we could just add S5 to each side. And so we could say S5 plus 1/6 is less than S, and S5 plus 1/6 plus 1 over 6 squared is bigger than s, the true sum. And we can compute that with a decimal if we would like. Let me bring up Desmos. So the sum from 1 equals 5, the sum of f of x from the first 5 terms is about 1.4636. And if I add 1/6 to that, I get 1.63028. And if I add another 1 over 6 squared, I get 1.65806. And so I'll switch back to my notepad here. We'll put all those pieces together. We know we computed S5. That's just the sum of the first 5 fractions. That's something you could easily do with your calculator. 1/6 is just one more fraction. And so we could say that 1.63 is smaller than the true sum, and 1.658 is bigger than the true sum. So the answer, whatever it may be, must lie in between those two values. Okay? So let's recap there, make sure we understand. We first derived this relationship that said not only can we compare a sum to an integral, but we can actually bound it between an integral and an integral plus one term. And then once we've got that, that means that we can look at the difference between a partial sum and the true sum and determine how far apart they are. And then with a little bit of algebra, we were able to then get the s term by itself and come up with a range of values for it. Now, you may be wondering, what is the answer? It's between 1.63 and 1.658, but what is it? Well, after much deliberation, Leonhard Euler finally proved the following. 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 and so on converges to pi squared over 6. Now, if you are wondering where that pi came from, well, you're not the only one. It's quite surprising that you add up a bunch of nice rational numbers, a bunch of nice fractions with integers on top and bottom, and somehow you get a pi squared out of it. But let's just check the decimal value for that. Pi squared over 6 is 1.6449. And if we go back to our range that we estimated, sure enough, it's right smack in the middle of that range. And so it seems very consistent with the argument that we made. If you're interested in learning more about this, how did Leonhard Euler actually figure out exactly what that approached? You can read about this on your own. It's a little bit beyond the scope of what we'll get to in this class. But if you Google the Basel problem, which is the name of this famous infinite series, and the question of what it converges to, if you find the Wikipedia article, you'll find a little bit more background information about where that came from.